Let's start off our third topic so far in our review of computer architecture. So this is still review at this point. As I said at the beginning of this class, if you know everything up to this point in the class, that's a requisite or a prerequisite for this course. We're just trying to blow through everything you should know in order to start the much more detailed content later in this course, where we talk about real processors you're going to be building. So things like out-of-order, multi-issue, multi-core microprocessors versus simple little processors you should have built in previous classes. So this is ELE 475 at Princeton University. We're talking about computer architecture. And today we are going to be reviewing caches. And this is the last topic, cache review, as I said, before we move on to new material. And the new material we're going to be moving on to very soon is superscalars, or processors which can execute multiple instructions per cycle. So let's take a look at the agenda for the cache review lecture. We're going to start off by talking about memory technology and motivate the different so we start off by talking about memory technology and use that as a motivation for caches. So we're going to look at different types of technology, DRAM versus SRAM, what the transistor technologies are behind them versus, or why we have these different memory technologies. Why don't we just have one? Why are there different ways to store information? Why do we just not use register files for everything or simple flip-flops for everything? Then we're going to motivate cache design, or why we have caches. So let's define what a cache is. A cache is a little piece of memory that you stick next to something which does not have all of the information that you're trying to store. Instead, it has a subset of that information, and hopefully it has a useful subset of that information. We're then going to talk about classification of these different caches. So we'll put names and labels on sort of different cache architectures. So we're going to talk about associativity of caches. We're going to talk about size of caches. We're going to talk about whether the cache has multiple things that could fit in one set or not. And we'll talk a bunch more about that. And then we'll have a very, very brief introduction to cache performance, or some of the things you should know about why caches give you good performance right now. Later in this course, we're going to actually have 2 more lectures about advanced caches. Advanced caches, we're going to talk about more sophisticated topics with how do you build and implement actual caches for very high performance processors. So let's start talking about memory technology. OK, so let's look at a memory, or something that can store multiple values and give us back some data. So here we have a very naive flip-flop-based register file. You'd probably never actually build this in a modern microprocessor. But let's look at the sort of conceptual idea here of what a memory really is. Here we have 4 entries that are flip-flops. Maybe it's multi-bit wide. So it's maybe, I don't know, let's say each of these registers are 32 bits wide, and each of these buses here is 32 bits wide. And we're going to sort of select, based on a read address, some value. So we can choose, this is 2 bits here. We can choose out of one of 4 places. We have write data that comes in, and we just sort of broadcast that to all of the registers. And we write depending on the write address here and the clock. And if the decoder tells us to light this up and the clock clocks the actual element, it'll load in the value. You may even have a write enable on something like this, where that would also feed, let's say, into the AND gates here. So it'll say, if a write's not occurring, don't actually load anything into these registers. OK, so that's really, really naive. Let's look at something a little more complex and how these things sort of start to actually look. OK, so now we're going to transition from talking about this naive register file and see what people actually build. And the first thing you should realize is, if you go to build something that's naive register file, you have lots and lots of bits as you add more and more bits here. Here we only have 4. But if we go to a 1,000-bit register file, this multiplexer grows really big. And if you stack these all up, 1,000 long, your aspect ratio, your x versus y, or the size when you go to lay it down on a piece of silicon is very long and very narrow. So you'll end up, let's say, with 1,000 bits, 1 bit tall. And that does not lay out very well, and it's not necessarily good for speed or from an area perspective. So why is it not good for speed? Well, it's not good for speed because wires have costs and take time to propagate. So if you have to propagate from 1,000 bits away or 1,000 bit cells away all the way over to the multiplexer, your cycle time is not going to be very fast. Versus if you were to somehow make it more square or more rectangular, the distances actually are minimized. So this is how we end up with arrays or memory arrays. And we're going to look at a memory array for a register file first. Let's look at a register file array and how you could possibly actually go build this, because it's a little bit different. We're not going to use fully complementary logic here for everything. Instead, we're going to start to transition to something where we will have more of analog circuits connecting our bits to respective buses. And we're also going to change how we do the decode. We're not going to have a full multiplexer here or a full decoder here. We're going to split that into different portions. So here we have an example array. It's a square. And each of these little boxes is a single storage element bit cell. And the address comes in here. And that goes up into a row decoder, which will turn on one of these wires at a time. And these are called word lines. And we'll have both read word lines and write word lines. And this is still just for a register file. But we're actually going to split out some of the bits here of our address and send it over to here, which is the column decoder. And that's going to choose, this column decoder is just a multiplexer very similar to this multiplexer, but it's going to only have a subset of the bits. Instead of having all of the bits that are together here going through this multiplexer and having n-bit address coming into it, it instead has a subset of that. So in this diagram here, we have a 4-bit wide readout or write. And we're going to have 1, 2, 3, 4, 5, 6, 7, 8 bits in bits across here. So we're going to need a 2-to-1 column decode. So this is a 1-bit decode here. But this is just a toy example. As we go to build sort of 1,000-bit arrays or megabyte arrays or gigabyte arrays or gigabit arrays, we're going to have lots of bits coming here and lots of bits there. But the idea I want to get across is you split off a portion of the address to the word line creation and a portion of the address to your column decode here. And in this register file, I wanted to just sort of walk through what this diagram over here, the circuit level diagram is. Here we have 2 cross-coupled inverters. And as you'll see, we don't have full complementary logic connecting these to things. But this is a stable storage cell. If you give this power, it'll store data. If we want to do a read, we need to connect the output of this to read bit lines. And these read bit lines are these vertical wires running here. And we're going to do this with effectively a pass gate here. When we energize the read word line, it connects the output of this gate, or output of, it's going to be this inverter here, to the read bit line. And if we want to do a write, we're going to turn on not the read word line, RWL here, but we're turning on the write word line, WWL. And what that's going to do is it's going to connect both the Q and Q bar to the write bit line. And now we get into sort of some analog magic here. But in order to have this work, what we're going to do is we're going to put we're going to energize or ground the right bit line such that it's stronger than what's going on of these two, or stronger than what either of these inverters can drive. So we overpower the inverter, and we can flip it, let's say, from a 0 to a 1 or a 1 to a 0. So this is not traditional sort of complementary logic, but this is how we typically build register files, small little arrays that are close, let's say, into a processor. Now let's move to something a little bit larger. We're going to look at memory arrays. So these are things like SRAMs. So we go from register files, something that we'd hold our general purpose registers for a processor in, and we're going to move out a little bit and talk about small arrays, something like caches, maybe a kilobyte of data. And these are typically built out of SRAMs. Same structure. We're going to change the cell a little bit here. The main difference is the cell, we're going to have two sets of bit lines. We're going to have bit and bit bar. And then we're going to have two pass gates here, and these are cross-coupled inverters in the middle. And by doing this, we also have this word line running the other direction, which connects this cross-coupled inverter to the bit lines. By having these SRAM arrays, typically what happens is because you have bit and bit bar, you can have these be even weaker than normal. And when you go to build something like an SRAM, down here, in addition to the column decode, you're also going to have what are called sense amps. And these are basically operational amplifiers where you hook the bit and the bit bar to them, and it can sense a very small difference between bit and bit bar. And by doing this, you can effectively have a very low difference between bit and bit bar and be able to sense it at the other side. And one of the differentiations I wanted to make between a register file and this SRAM here is that the register files many times are designed to be sort of multi-ported. But in this diagram here, these bit lines get reused. They're both read and write bit lines. So we've effectively built a single-ported SRAM. Having said that, people do build multi-port SRAMs and single-ported register files, but conventionally, you build a register file when you need speed, and you need lots of ports, and you build an SRAM when you want to be more dense in your storage. OK, so now let's move to a piece of technology that is in all of your computers, or rather register files and SRAMs are all in your computers. But this is something that you can actually see, because usually the SRAMs and the register files are all integrated onto your centralized microprocessor. You don't actually get to go see it. But here we have a stick of DRAM. So let's see what this is. This is PC100 DRAM, and this is old stuff. This is 128 megabytes of RAM. Nowadays, your computer has, at least this laptop here, has 4 gigabytes of DRAM. And different people have different amounts. But DRAM, I want to contrast with SRAM. You still go and build an array out of it. But the actual storage looks very different. The bit cell storage, instead of being some form of cross-coupled inverters, instead, you're going to have one transistor which hooks a capacitor into your bit line. Now, you may ask yourself, how do you build a capacitor? Capacitor, typically you need, 2 plates or 2 pieces of metal with some dielectric in the middle, where you can store charge. Well, what's inside of that RAM looks very odd. It is a capacitor, but it's a very oddly shaped capacitor. Typically, what will happen is you build these very, very deep trenches, very long and skinny trenches. They're skinny because you want to put them very close together, because if you want gigabytes and gigabytes of RAM, the smaller you make it, the more you can shove on a single piece of silicon. But you have these really long and narrow trenches here, and you have 2 plates of metal and then a dielectric in the middle. So in this case here, we have, I think there's 2 metal sort of plates here, and then there's some dielectric sort of shoved in between there, but you can't really see it on this picture. And then all the actual logic is up here. So in this diagram here, this is the transistor, N doped, N doped, and here's the depletion region, and here's our word line. But basically, that's this transistor here. So we're going to be connecting the capacitor, which has a very funny aspect ratio, it's very tall, to this bit line. And to give you some idea, this is a slice through the silicon wafer. This is not a plan view or top view. Top view, you would just see what looks like a transistor and then some poly plug here running vertically. It would look really small. But this is a slice. And the reason we do this is because we want to see that the actual capacitor is very long, very deep into this. And one thing I wanted to point out is this is typically really hard to go build on your standard CMOS process. So this is hard to go build on something like a logic process. You have to go build this, let's say, in a special DRAM-only manufacturing process. So you want to, it's sometimes hard to mix that. There are some technologies which allow you to mix them, but when you do that, people haven't really designed ways to make them as small, the DRAM cells as small. OK, so what are the advantages of DRAM? Why are we even talking about DRAM? Well, it's a lot easier in DRAM to have large amounts of storage. You can have big amounts of storage in the same area. Because instead of having, I don't know, in SRAM, 6 or 8 transistors for each cell, instead, we now have 1 transistor and 1 capacitor. So it's actually less. Now, how does this circuit work? Well, logically, what we're going to do is we're going to store data or store charge in the capacitor. So we're going to connect the capacitor to the bit line. We're going to either put a 1 or a 0 on the bit line. And then we're going to disconnect it. And it'll hopefully store the charge. And at some point in the future, we're going to connect it. And we're going to discharge it into the capacitor into the bit line and read out the value. And we still need something at the bottom here, which is very sensitive to be able to read out this bit. And the reason is because the capacitance that you can store in one of these little capacitors is a very small amount. So there's not a whole lot of charge in the circuit. OK. So what is the cell? What's the problems with this? Well, first, one of the major problems with this is you're going to end up having this capacitor discharged and charged. And capacitors, as you may recall, don't always store their charge that well. They might slowly lose that charge over time. And what this turns out to be is you're actually going to have to refresh the DRAM. So you might have heard of DRAM refresh. But typically, in a modern day computer, your DRAM will only hold the data for maybe a few seconds. It used to be that it only held it for a few milliseconds. Most RAM is actually decent now. And you've probably seen some attacks that people have built around this. Like there's some encryption attacks where people will effectively turn off a computer and then pull the RAM out and stick it in a different computer. And the DRAM will still hold the charge, still hold the information, even after you remove the electricity or remove the power from it. Because this is a bunch of little capacitors that will store that charge. That's a funny little case where this DRAM ends up being a negative. But we're really doing this to have more space to store data, because each of these bit cells is a lot smaller. OK, so I like this diagram. And this is one of the more key diagrams in today's lecture here, is showing the relative sizes of SRAM versus DRAM and different types of SRAM versus DRAM. So let's start off here with an SRAM cell built out of logic, on a logic process or logic CMOS technology. So that's this one here. This looks to be 6 transistors, so sort of optimized SRAM on a logic process. And it's pretty big. Let's contrast that, though, with this one over here. We have DRAM on a memory-specific process. And it's tiny. So it's not only 1 transistor versus 6 transistors. It's actually more than 6 times smaller because they can optimize it because they can go into the Z dimension here, go into and out of the board, because that trench capacitor goes down into the substrate. And some other interesting things on this diagram here, we have a DRAM on an ASIC process, or DRAM on a traditional ASIC process, which is here. Here we have 6 transistor cell with local interconnect. It's a little bit smaller, so what that means by local interconnect is you can use the poly layer of your process, or the polysilicon layer, to do interconnection, so you don't have to use wires for everything. So it gets a little bit denser, so the layout gets a little bit denser. And I really like this bottom one here. Yep, the bottom one labeled A is not 4 different things. Instead, what that is this is a fully complementary logic cell, a storage cell built out of gates. So there's some number of gates put together here. So what this is trying to get across here is that the addition of custom logic cells, either this one or this one, storage cells in your library is really important, because otherwise your RAM is going to be a lot larger, or you won't be able to fit as much memory on your machine. OK, so to wrap this memory technology section up, I want to talk about some of the trade-offs. And computer architecture is all about the trade-offs. And why would we use one type of technology versus another type of technology? So what are our trade-offs here? Well, we can go from fast, close, small things, so things like latches and registers, and we sort of put them together into bigger, we put them together into bigger things like something like a register file, and then SRAM, and have different technologies even. And as we sort of get to bigger and bigger memories, we get a lot more capacity, but it takes longer to access them, kind of by definition. And typically we have less bandwidth. But if we have small things, we have low capacity, low latency, and very high bandwidth. So it's sort of a trade-off of capacity versus the other positive aspects. And depending on where you put it in your memory system, you might want to trade these off differently.